Ladies and gentlemen, we're going to continue our exploration of Chapter 3. And Chapter 3 is about chirality. Greek word for hand is chiron. And so objects that are handed, like our hands, are called chiral. What makes them special? Well, here's a right hand, it's handed. And it's the mirror image of, you guessed it, my left hand. It's also chiral. How do I know it's chiral? Well, I try to put them on top of each other, and the parts don't match up. I got a pinky underneath a thumb, and a thumb underneath a pinky. Need to say no more because they're different. So two objects that are not superimposable mirror images of each other. Superimposable means if I put them on top of each other, they all match up. And here they're not matching up, so they're non-superimposable. And they're clearly mirror images. Each one of those molecules is handed, which is to say chiral, same thing. And the pair of them that are related as mirror images are called enantiomers. Very nice. So our activity is going to illustrate that word and another new word. And we've got a lot more notes in the morning lecture, so you want to look at those. We don't need notes over and over again. We got a question in the back.
Yeah, I have a question. So you have your hand and you have one hand, so your hand up. Okay.
Okay, they're related. He's talking about hands and stereo centers. Hand is just a nice example. It's not a molecule, but you can pretend it's like a molecule. It's got a stereo center with 4 different things on it. Sure.
Okay. So when you switch it, okay, why you have to change it and the dash on edge?
Well, you don't have to switch anything. Switches are tricks. They're not chemistry. They are tricks to let us do what we want to do without having to rotate things in our mind, which is very difficult for a lot of people like me. Okay. So I give you tricks. A single switch will switch the stereo center from R to S if it was R, or from S to R if it was S.
Okay.
That's what single switch is good for. So we're going to use that today. And a double switch is good for nomenclature only.
Yes.
Name that stereo center. That's the only thing the double switch is for.
But the dash will always be dot, but the edge will be off. Now you don't switch them, right?
Well, switches just find the dash and put the number 4 there and switch with whatever group was there, okay. And then switch the other 2. There's your 2 switches to get RS. Okay. That's what RS, double switch is good for. Single switch is good to create a new stereo center. And this problem is about drawing all possible isomers. It seems to me that a single switch would be a good trick to get a new stereo center without having to think at all. Yeah, we don't like thinking if we don't have to. Sorry?
Make more.
Oh, you're asking how many molecules maybe? Yeah. Yes, that one thing you might want to know is number of stereoisomers. It's not really part of the activity, but it helps us get started. And I don't think I'm sharing right now. Sorry about that. Oh, I got my share. Sorry. Number of stereoisomers is 2 to the power of n. I'd like to remind you it's 2 because there's 2 choices for each stereo center, R or S, and n is the number of stereo centers. So in our molecule here, that's going to have a stereo center on carbon 1 and a stereo center on carbon 3. N is 2. You're going to draw 4 molecules because your goal is to draw all your stereoisomers. Okay? So here's our molecule. We're going to start by drawing cyclohexane. Cyclohexane in blue. And we got carbon 1, carbon 2, carbon 3. On carbon 1, we have a how do you know it's a trichloromethyl group? How do you know it's not a ditrichloromethyl group? One, that doesn't exist, but there's two numbers in front that indicates two identical groups. That's what your die is for. When you have two numbers, you need a die for two of the same group. And the group is called trichloromethyl. So we got a CCl3 here and another one on carbon 3. And what other group is on 1? Isohepto. That's 6 in a row. 2, 3, 4, 5, 6. That's 7 minus 1 is 6. And then you put the V at the end to get 7. And don't forget, when I have a stereoisomer problem, I need to see all 4 groups on every stereocenter. Always. So there's your groups. We have a strategy for making sure we have R for 1 and S for number 3. You do your 1, 2, 3, 4. Goes like this, this. And yes, this thing hits a branch before this thing. We wanted it to be R, and if I connect 1, 2, and 3, it's already clockwise. That means we want a number 4 on what? A dash or a wedge? Dash. Yeah, dash. We'll put it in purple. Make sure your dash goes all the way. And adjacent bond wedge. And we start over, but our other stereocenter needs to be S. The one on number baby blue. 1 for trichloromethyl, 2 for the same as 2 before, 4 for an H, 3 for a C that hits the branch later. My goodness, we were lucky because this one's supposed to be S and it's already counterclockwise. So 4 on a dash. I didn't have to be lucky. If it gave the wrong direction, I just put the 4 on a wedge. There you go. You got 2 points for the drawing, and I'd have to give you another point for doing your stereocenters, right? Cool. Draw its mirror image and label each stereocenter as R or S. I just have to point out one thing before I do this. This is called a right hand. Its mirror image is drawn like this. Pretend there's a mirror between them, and it's called a left hand. If you drew an R stereocenter, guess what its mirror image is going to be? S. If you drew an S stereocenter, guess what its mirror image is going to be? R. I think we're ready. Drawing a mirror is a good idea. It's not mandatory. There's many ways to answer this, but if you have a mirror right beside it, it's an imaginary mirror, and just draw the mirror image the same distance from the mirror. That one is pretty straight across, up to a corner. Yeah, and then this. Always describe your bonds relative to the mirror. So describe how you draw this wedge relative to the mirror. Is it away from the mirror or towards the mirror? This bond right here. It's leaning to the right where the mirror is. Towards the mirror and up. Do you agree? Let's draw a wedge towards the mirror and up here. I use the same word. Towards the mirror and up. So you see how I'm helping you out if you're like me and you have trouble visualizing? Just describe things relative to your mirror. There you go. And then it looks like this wedge is pretty much straight down off 3. Let's do it straight down off 3. And it's got a CCl3 on it. And the H, it's on a dash, away from the mirror, and a little bit down. It's on a dash, a little away from the mirror, a little bit down. And I want to remind you the stereocenter 1 was R, and the stereocenter 3 was S. Guess what the mirror image of the purple S is? Guess what the mirror image of any S is? R. What's the mirror image of the red R? S. Congratulations. So your four possibilities are, with stereo center 1 being listed first and stereo center 3 being listed second, we've got two of them. We got RS and SR. I think the only two we're missing are SS and RR, and then you're out of possibilities, right? Yeah. Hey, this question is written as the protocol for the test question, which is on the next page. Well, it will be on the next page, activity 2. But this has it broken down into the steps you should be considering for doing your question. So you're going to draw its mirror image, labeled, done, and I copy your first molecule except to a single switch on one of the stereo centers. So if I chose this stereo center to do a single switch on, it's going to become what? This one down here. It's going to become R. And I'm not going to touch this one at all because I want RR. It's a new molecule. Please don't do a single switch on both. You will have drawn this same molecule in a different way, but it will be the same molecule. I can't give you credit for it. If you drew another molecule that was 1S, 3R, like this, you get no points for it and no points for comparing it to anything else because you just drew the same molecule again. I need 4 different molecules. So follow the instructions in I. I'm copying here. I'm copying the top stereo center as is. No changes. 1, 2, 3, 4, 5, 6, 7. Oh, no, not step 6. With a V. And down here, I'm going to put the H on the end of this stick. It's a wedge. And on the dash, a CCl3. The new molecule. Top one was R for red, and the bottom one was S. Now it is R. Why? Because I did a single switch. And I labeled draw the mirror image, and I labeled the stereo centers. And then I'm going to, no, I didn't do that yet. I did this. I copied my first molecule with a single switch. Now I'm going to draw the mirror image of part C. That would be part I. I didn't edit that out. There you go. And label each stereo center as RS. Okay, well, we're getting practice with drawing mirror images. Let's see, same distance from the mirror. I'll start with the cyclohexane this time. My computer decided to start ignoring me. Okay, thank you. All right, wedge towards the mirror and the up. CCl3. Dash towards the mirror pretty much straight across. 2, 3, 4, 5, 6. And down here an H almost straight down. And a CCl3 away from the mirror down. And the mirror image of the red R is a red S. The mirror image of purple R is a purple S. Congratulations, you have 12 out of 18 points. The hardest points were the first molecule. After that, with the system we have, it gets easier and easier. And then the 6 fastest points are at the end. Let's see who remembers. What do you call a pair of molecules that are not superimposable and mirror images of each other? Is it enantiomers or diastereomers? They're enantiomers. And we'll write that in exciting gray, normal gray pen. We'll use gray enough. Enantiomer. It says upstairs you're allowed to use the short form E. So non-superimposable mirror images. As a result, every stereo center is the opposite. And then we'll deal with diastereomer. Diastereomer. Some of the stereo centers are the opposite, comma, some are the same. And what's that the definition for? Diastereomer. Not the same as an enantiomer, it's an enantiomer. Okay. So, get our little highlighter here, pink. There's a pair we haven't compared yet. Yeah, and here's a pair we haven't compared yet. And here's a pair we haven't compared yet. And of course, here's a pair we haven't compared yet either. You like that? Got a nice traffic jam. Those are all molecules where one of the stereo centers changed and the other stayed the same. So here the red stereo center stayed the same. The purple changed. Here going across down diagonal, red changed, purple stayed the same. Here, going here to here, red changed, purple stayed the same. And going here and here, red stayed the same, purple changed. And those are all called, what are they called? What's D stand for? You don't want to say it, huh? Diastereomer. And that's that. Now you got 18 points. You did 6 comparisons, 1 point each. The molecules drawings were 2 points each, that's 8. So 6 is 14. And each stereo center is half a point. Usually they're worth more than that. You did all your hard work up here, and then it was easy after that. So I figured compensate. So there you have it. We're going to do another version of this that looks more like your test. But the next one will not have 4 molecules for a very strange reason.